All right, how's everyone feeling? Wouldn't you agree? Any questions, needs, concerns, etc. before we get started? All right. Main thing I want to do today is start talking about, introduce the concepts we're going to cover for the next month. Before that, though, the last thing we discussed on Monday was angular momentum. So we'd just like to pick that up again briefly to make sure that how the math for that works makes sense with everyone. And then we're going to take a break from rotation for a while. Angular momentum is the notion that, kind of like how linear momentum describes how much something wants to keep moving forward in a straight line. If something is spinning, it has momentum that is telling it to keep spinning at exactly the same speed in exactly the same direction, and also around the same axis. If something is rotating from your direction clockwise around the z-axis, it wants to remain spinning in that direction and also around the same axis so badly that it will refuse to change. At least it won't change away from the z-plane. And angular momentum, like linear momentum, is conserved, meaning that if you somehow manage to change your rotational inertia, the angular counterpart to mass, you can adjust your angular velocity accordingly. Your angular inertia and your angular velocity will always multiply together to create the same number, which I attempted to demonstrate by sitting in this chair, holding out these weights, spinning, and then partway through pulling the weights in, drawing the mass closer to the axis of rotation, reducing my angular inertia, and speeding up because of it. I hate it every time. Somehow the dizziness is not going away. Those concepts sound familiar and feel all right? All right, so let's very briefly make sure that you can demonstrate the basic math for that concept. Angular momentum is angular inertia times angular velocity. So let's say that for simplicity's sake, when I am sitting in this chair with my arms fully extended, my angular inertia is 1, just for simplicity's sake. And that while I am spinning with my arms fully extended, my angular velocity is 1 rotation per second. So my angular momentum, using those units, would be 1. 1 times 1 is 1. Now, when I pull my arms in, let's say that that is going to cut my angular inertia in half, because I am pulling the mass closer to the axis of rotation. It is easier to make me spin, and therefore that makes my moment of inertia lower. What numerical effect does that have on my angular velocity? On the chair, when I pulled my arms in, did I speed up or slow down? Speed up. And that's because my angular momentum needs to be the same. Angular momentum is conserved. This value never spontaneously changes by itself. It takes effort to make it change. Like our normal momentum tells you how much effort it takes to stop something that's moving. So this is the amount of momentum that I have. And so if I cut my moment of inertia in half, what does my velocity have to become so that my angular momentum remains constant? 2. Very good. If I cut one thing in half, the other has to double such that they still multiply to the same number. Sound all right? Okay. Now, one last hypothetical. Let's say instead of pulling my limbs in, I magically acquire more mass in my hands somehow. Like, wizard steps in and the weights in my hand become 10 kilograms instead of 1 kilogram. So rather than pulling my limbs in and decreasing the distance between the mass and the center, I am increasing the amount of mass, keeping it the same distance away. That would make my moment of inertia go up, because there's now more matter further away from the axis. So if my moment of inertia, instead of decreasing, increased to 3, what would that make my rotational velocity? 1/3. Very good. Again, they have to multiply together to create the same number. And so 3 times 1/3 gives you 1. If you somehow triple your moment of inertia, your angular velocity will get cut down to 1/3. Inversely, if you reduce your angular inertia to 1/3, you will triple your rotational velocity. Again, this is the sort of thing that figure skaters intentionally employ to make themselves spin faster, pulling their limbs in, and then throw their limbs back out to spin slower and start skating in a straightish line again. Although I suppose, and again, this is me making Taekwondo references because I did that for a lot growing up. Spin kicks in martial arts do something similar. You tend to pull your leg in to spin faster, and then when you are ready to stop spinning, you throw your leg back out and kick. Oh, that was a pretty poor demonstration. Something like this. Pull your leg in to spin around and then kick out. So, several physical activities use this principle. Questions before we stop talking about rotating things for a little while? All right. Now, kind of information about my course planning process. This course is based on a specific textbook in terms of the order things get taught in and what sorts of questions I have you do that come from that book. And within that book, the chapter that we just concluded for rotation is labeled as Chapter 8. And what would then be labeled as Chapters 9 and 10 involve gravity and orbit, sort of applying gravity as a centripetal force, causing the orbit of things like the moon around the Earth and the Earth around the sun. We will talk about that. However, I kind of want to step away from rotation for now. We've been talking about it for a while. I want to start talking about some other things so that I can also have you do labs about some other things. And instead, to that end, we're going to kind of jump from what the textbook the course is based on calls Chapter 8 to what it calls Chapter 11, 12, and 13. So we're kind of skipping over a little bit of gravity and orbit to come back to it later, specifically because there is a celestial event coming up that involves gravity and orbit, because there's going to be an eclipse on April 8th. And so I'm planning a whole day/week of stuff around the eclipse as we get to that point. So I'm kind of skipping through the orbit stuff for a second so that we can talk about some other things for a while, get a break from rotation, and then have some different sorts of labs. And then we're going to come back to it when it's most relevant for Eclipse Day. Does that sound fair? All right, cool. So the chapter numbers on the slides are going to be, they're skipping around for that reason. I guess I feel the need to explain myself anytime something like that happens. So that is why the new notes that I'm about to present say chapters 11 and 12 instead of 9 and 10. Now, after we took test 1, I did say that the second half of the class would be talking about some weirder stuff. First half of the class was all about linear motion and force. Then after the test, we started talking about rotation, the weirder version of motion. And we're going to continue talking about more different sorts of topics. The main things I want us to work on here in the latter half of the course are pressure, waves, and electricity. 3 things that are pretty important to living on planet Earth, because pressure from the air contributes to us being alive. It creates our atmosphere, the oxygen around us we need to live. It's important to understand air pressure and also water pressure, because air and water are very important things on this planet. Waves are important because they affect your senses of sight and hearing, and electricity is important because, well, look at the infrastructure we built for ourselves. So those are the things that I want us to discuss in the latter half of this course. And to get to those points, chapters 11 and 12 are kind of reviewing, and I do expect most of today to be a review. Reviewing matter rather than motion. Because up until now, pretty much everything has been about motion in some way, shape, or form. We talked about motion itself, the forces that cause motion, the energy that happens when things move or you make things move, the exchange of energy, rather, and then rotational motion, which is still a form of motion. Everything up till now has been about motion itself, how matter moves. But we haven't talked a whole lot about the matter itself. So I want to take today to define matter, make sure that the concepts that you're going to need to know about matter itself are fresh in your brain, that you remember them and they make sense, before we start looking at how matter reacts to pressure, waves, and electricity. Because all of those things are tied into what matter is. Pressure is matter, acting on other matter, specifically how we're going to look at how fluid forms of matter create pressure on solid forms of matter. Waves is about how matter moves in a oscillating pattern to create the wave. And then electricity is still technically moving matter, because electricity is made of electrons and electrons are made of matter. So before all of that, we're spending today going over what matter is, different forms of it, and what we need to know to then discuss those concepts. Does that sound fair? Okay. Now, again, I'm hoping a lot of this is review. In physics, we like to define things. So to quickly define matter, which I'm not sure if I've done yet, everything in the universe that has some form of substance is made up of matter. Matter is all physical material, solid, liquid, and gas. If something has mass, it is made of matter. So mass is how we measure matter, like how length is the concept and meters is the unit we use to measure length. Matter is the concept and mass is the unit we use to measure it, for example. And kind of scaling all the way down to the smallest parts of matter and then building back up to the bigger concepts. Smallest forms of matter are atoms and the things that make them up: protons, neutrons, and electrons. Questions before I change slides? All right. So again, just to redefine what matter is made up of these things: atoms comprised of protons, neutrons, and electrons. All atoms have at minimum one proton involved. Protons and neutrons live in the nucleus. That's the core of the atom at the middle, and that's where most of its mass is contained. Electrons aren't part of the nucleus. They instead orbit the nucleus, like how the moon orbits the Earth. So this part right here is most of the physical stuff of the universe. Protons and neutrons are the matter, the mass of the universe, broadly speaking. But every atom, and therefore all matter, is made up of some amount of all of these things. To review the particles themselves, protons are the positively charged ones. They live in the nucleus and they have they're tied for the most amount of mass. Neutrons also live in the nucleus, and those are the neutral ones. It took me a weird amount of time to wrap my head around this one as a kid, but neutrons are not the negative ones, they are the neutral ones. They have a zero charge, whereas protons have a positive charge. They have no charge, but they are tied for having the most amount of mass. It's still not a lot of mass. Protons and neutrons both have mass in units of kilograms times 10 to the negative 27th. So they're still tiny, but they're tied for the biggest of the tiniest. And then there's electrons. These are the tiniest. They have the tiniest mass. They're about 1,000 times smaller than protons and neutrons. And these are the negatively charged ones. Electrons are the negatively charged ones, and we call them electrons because they are what make up electricity. Electricity is made of moving electrons because that's the only part that can leave the atom. Protons and neutrons are stuck in the nucleus. The electrons are spinning around it, they're free to leave, and so their negatively charged motion is what forms electricity. So electricity, electrons. Make sense? All right. Parts of the atom sound familiar? All right. Individual types of atom comprise the elements that make up the universe. We've sorted those elements into a nicely organized table. To reiterate how the atoms affect the element, this is not a chemistry class, so you don't have to memorize any of the elements, but physics is still about the universe. The elements make up the universe, so it's still important to understand the basics. Protons determine element. Number of protons determines the element of the atom. And the number of protons correlates directly to the number of an element on this table. The first element, number 1, is hydrogen. Hydrogen has 1 proton, and that's why it's number 1. Helium has 2 protons because it is number 2. Proton number is directly tied to element number on this table. I want to make that one clear. The other 2 particles then affect basically the flavor of what element you're dealing with. Neutrons don't affect element, they affect isotope of that element. For example, hydrogen has 3 isotopes. There's hydrogen with no neutrons, hydrogen with 1 neutron, and hydrogen with 2 neutrons. They're all hydrogen because they all have 1 proton, but they all have slightly different properties based on the number of the neutron. It really is like flavor of that one element. They all react slightly differently. So changing neutron number doesn't change element. I want to make that one clear. Meanwhile, changing electron number also does not change element. The number of electrons determines the charge of the atom. Because the protons, the positively charged ones, are stuck in the middle. You can't change something's charge by changing the number of protons, because then you're changing the element and you're undergoing a nuclear reaction and you might blow something up. If you want to change something's charge, you instead have to change the number of electrons spinning around it that counteract the positive charge of the protons. If you want something to be neutrally charged, it has to have the same number of protons as electrons. If you want something to be positively charged, it needs more protons than electrons, more positives than negatives. And then the inverse, if you want it to be negatively charged, it has to have more electrons than protons. So if you, for example, on a cold winter day, generate a lot of static buildup in yourself, that means you have now acquired more electrons than you have protons. And you have built up a negative charge, and when you touch something and you zap, that is you getting rid of all those electrons you don't need until you neutralize yourself and have the same number again. Make sense? Sound good? All right. Now again, not a chemistry class. You You don't have to memorize anything about this table, but it's still useful to understand the basics of how it works. So just to practice that. If I had an atom with 6 protons, what element is it? If you don't know what they all stand for, that's fine. You can just tell me the letter. Carbon, very good. Number 6 is C for carbon. You find an atom with 8 protons and 6 neutrons, what element is it? Oxygen, very good. The 6 neutrons does not determine element, only the 8 protons does. Lastly, you find an atom with 11 protons, 12 neutrons, and 10 electrons. What is the net charge, the sign of the charge of that atom? Positive, very good. It's positive because it has more protons than electrons. The element would be Na for sodium. Is that all right? All right. Again, not a chem class, but it's still useful to know a few things about this. So, a brief amount of chemistry things that I enjoyed in chem class and find it useful to know, just kind of as a brief aside. The vertical stacks on this thing represent families, and families tend to have similar traits. So elements that are vertically aligned usually are pretty similar to one another, and that's why the columns all are color-coded by column for the most part. There's a few exceptions to this rule, though. Hydrogen may live on top of lithium, but hydrogen and lithium do not have the same properties. They're separate families, and that's why they have a separate color code. Hydrogen lives by itself. There's nothing in the universe with the same properties as hydrogen. And also, based on the color code, you got 2 families that kind of live on top of each other on a stair-step pattern here in the center. But other than those 2 exceptions, vertical columns tend to have the same properties. The far right column, helium down to Og, which I don't actually know what that stands for. Those are noble gases. They all behave the same in that they do nothing. Literally, the noble gas family, including helium, never does anything. It just exists. It doesn't react at all. And that's why you can technically safely inhale helium. It doesn't do anything in your lungs, and that's why you just exhale it when it makes your voice squeak. That does not mean that you should huff xenon, though. As an opposite example, on the literal opposite side of the table, the column from lithium down to francium, those are all called the alkali metals, and their most famous shared property is that they explode in water. If you have a chunk of lithium and you get it wet, it will combust. You don't even have to dunk it into water. Frankly, the water in the air will make it start reacting. And that's why you don't throw batteries in the pool, because they have lithium cores for the most part. Sound good? All right, last fun-ish fact, in my opinion at least. Something that always confused me as a kid is why the letters, the abbreviations don't match the name about half the time, and that's because the abbreviations all come from Latin, most of them. Iron is Fe because the Latin for iron is ferrum. The Latin for silver is argentum, so it's Ag. The Latin for gold is aurum, so it's Au. And then Mercury doesn't actually use Latin, it uses Greek. So Mercury's old-fashioned name is Hydrargyrum, or something to that effect, and that's why it is Hg. So that confused me as a kid anyway. More review. Atoms do tend to bond to things. If it's unbonded or it is only bonded to itself, we consider that a pure element. So H2 and O2 we consider pure elements because there's only one type of nucleus present, even though since they're bonded they are molecules. So molecules does not always mean compound necessarily. It's kind of like how all squares are rectangles, but not all rectangles are squares. All molecules are made up of multiple atoms, but multiple atoms does not always mean multiple elements. So if it's just one letter code, it's just one element, even if it's a bonded molecule. And then things start getting weird when you do start forming compounds of multiple elements, because that tends to change their properties entirely. Most things in the universe are actually compounds, because at this point in the universe's life cycle, most of the elements have found something to combine with. There's very rarely pure elements in nature anymore, except helium, because it doesn't bond anything. Some pretty common compounds include water, rust, and carbon dioxide, which have very different properties to the things that make them. For example, CO2, carbon is important because we're made of it. O2 is important because we breathe it, but CO2 is poison. That's the thing you exhale. You don't want too much of it. Rust is made of iron and oxygen. Iron is durable, oxygen keeps us alive, but rust is fragile and poisonous. The universe is really, there's a lot of poison in the universe, as it turns out. I think probably the best example, which I failed to put on my slides, is salt, sodium chloride. Sodium by itself is explosive. It's one of those metals in that far left column that blow up. Chlorine is flammable, poisonous gas that will burn you and poison you if you somehow are exposed to it. But somehow when these two things combine, they make rock salt. I've always found that interesting. But yeah, your table salt is made out of poisonous dynamite. Now, questions? Okay, so why does all this chemistry stuff matter to us in this physics class? It matters because different materials at different temperatures and pressures are different states of matter. And as we start talking about things like pressure and waves, understanding the differences between the states of matter, what material you're dealing with, and the properties of that material are going to affect how it reacts to pressure, waves, and electricity. So all those different elements and compounds exist at different states of matter based on the temperature, solid, liquid, and gas, all the classic ones. Turns out though, there's actually 5 states of matter, not just the 3 that you're used to. The 4th state is plasma, which you might have heard of. Plasma is technically what's in the light bulbs right now. It's what happens when you take a gas and you heat it up and electrocute it and it starts glowing. It's also what the sun is made of. And for that reason, plasma is actually the most common type of matter in the entire universe, because most of the mass of the universe is in stars and nebulas and not, solid planets. On Earth, though, we're mostly dealing with solids, liquids, and gases, and so those are the 3 we'll deal with the most. Now, things to note about solid, liquid, and gas. In physics, we consider solids to have definite shape and definite volume. Definite shape means this hexagonal cylinder of iron is not spontaneously going to assume a different shape by itself. Not on its own will it ever become anything other than this hexagonal cylinder. If I want to reshape it, I have to undergo some sort of a process to make that happen. Likewise, definite volume means it's never going to get any bigger or smaller by itself. This is its shape and its size, and that's not going to change on its own. That is different to liquids and gases. Liquids do have definite volume, meaning a gallon of water is not spontaneously going to take up more space than a gallon by itself. But liquids don't have definite shape, meaning if I pour a gallon of water out of my jug, it is no longer the shape of the jug anymore. It takes the shape of whatever I pour it into. Water can flow. Liquids can flow, not just water. And that is a pretty big difference to solids. Since solids don't really flow, since they tend to retain their sense of self, we tend to constantly be submerging solids into liquids rather than the other way around. And that is going to be important in our discussions of pressure, because when you submerge something into something else, like liquid, the liquid starts exerting pressure on that thing. So solids tend to have pressures exerted upon them by the fluids they are submerged in. Make sense? Does that not make sense before I move on? Okay. Now gases are similar to liquids in that gases also have no definite shape. They also flow. They take the shape of their container. But gases also have no definite volume, as it turns out. Unlike water, which if you compress it, it doesn't really get any smaller. You can take a gas and squeeze it down into a smaller size, and that's what happens when you go to a party store and buy a helium tank. Those helium tanks have like a sports center full of helium jammed down into the size of the container. So you can compress a gas to make it smaller, unlike a solid or a liquid, at room temperature. Main thing we care about gases, though, is that they also, like liquids, have no definite shape and they can flow. And for that reason, we consider both liquids and gases to be fluids, and solids are their own thing. Liquids and gases are both fluids, and that means we are often submerging solids into liquids and gases. Technically, you are submerged in a fluid right now, because air is a gas and gas is a fluid. So you are submerged in air, and that's why you are subject to air pressure. Make sense? Okay, so that's why the state of matter is going to matter, pun not intended. State of matter is also going to affect things such as volume and surface area. Solids have definite volume, so just to define volume very quickly, volume is the amount of space something takes up within three-dimensional space. Every different shape has a slightly different volume formula. You never have to memorize any of these. I'll make sure you have them. Your formula sheet should have some of them on it already.
Conversion factors, speed, pressure, power.
I need to add that page before the exam. But I'll make sure you have any volume formulas you need. But just to review a few. Cubes, length times width times height tells you its volume. As long as it's a cube and all those sides are the same, that'd be A times A times A, which is A cubed. And then cylinders and spheres have their own formulas. I'm only bringing up the cube because we're going to use that one in a second. Every day I come in here, someone moves my markers around and I never remember which ones have ink in them. Not that one either. Better. So, volume is the amount of space something takes up. This is different to surface area. I need to define surface area now because, again, pressure is what we're going to be talking about next out of that list of concepts I mentioned, and pressure is going to end up depending on both. So I want to define the difference between volume and surface area. Volume is the three-dimensional space something takes up. If something's volume is 1 meter cubed, it takes up 1 meter by 1 meter by 1 meter of space. Literally, it's a cube of those dimensions. That is different to surface area. Surface area is the total lump sum of all the flat areas on the surface of the item. That's why it's surface area, the total area of its surface. If I asked you to tell me the surface area of a cube, what's the area of one face of a cube? length times width. How many faces does a cube have? 6. Now, if it's a cube, all those faces should be the same, right? If it's a perfect cube. And that means that the formula for the surface area of a cube is 6 times length times width. Since length and width are the same on a cube, a times a is a squared. So it's 6 times a squared because there's 6 faces being added together to create that total amount of area. These are different things. This is a flat surface, square footage, literally, because length squared is area, and volume is length cubed for 3-dimensional space something takes up. And something's volume versus its surface area is going to affect how it responds to pressure. Questions thus far? Okay. Now, why do we care about volume versus surface area? We care about volume because volume is a part of something called density. And we were talking about elements and compounds earlier, so going back to that, the density of any substance is how much mass is jammed into the volume of that substance. So this lump of iron, for example, there is a certain amount of iron atoms physically jammed into this cylinder, and the density of that iron is its mass over its volume. So density is the stuff contained within the 3-dimensional space of the item. And we're bringing up elements and compounds and stuff because any given substance always has the same density. If I had 2 different pieces of iron, they could have very different sizes and masses, but their densities are alike because they're both iron. There's the same amount of iron atoms per unit volume. So if I had, twice the volume of iron, its mass should double as long as the density stays the same, because it's the same type of material. Does that sound all right? So volume effects is a part of density, and therefore volume ends up determining something's volume and density combined end up determining the mass of something. Because what something's made of doesn't usually change. Like, this is iron, and that's not spontaneously going to change on its own. And iron always has a specific density. So it doesn't matter how much iron I have, the density here, and this is the density symbol, which is frustratingly the same symbol as momentum. I'm going to try to label them differently on the form of the sheet where applicable. But this formula is the density formula. Density is mass over volume. Iron has the same density no matter which piece and size of iron I'm looking at. So since this doesn't change for iron, the volume of the iron ends up determining the mass of the iron. Basically, if the density is always constant, I have 3 times as much volume of iron, I'll have 3 times the mass of iron. So volume and density end up determining the mass of something. Questions thus far? Okay. Now this is different again to surface area. Volume ends up affecting mass, whereas surface area ends up affecting how something responds to pressure, because the bigger something is, the more surface area it has. Actually, I'll put this here now that I think about it. The more space, the more faces that thing has for pressure to act on it. The way that pressure is going to work, and we'll define this later on, I'm just kind of getting ahead of myself now. The way that pressure works is like say the pressure from the air on you right now, the air is literally pushing inwards on your entire surface area. So the more surface area something has, the more space there is for, you know, a fluid you're submerged in to exert pressure on it. The bigger something is, the more area the pressure can act on, and therefore the more force something usually gets from that thing. This is why we don't usually make submarines very big, because deep down at the bottom of the ocean, a really big submarine has a lot of surfaces for the water to crush it, for the water to exert pressure on it over. But the smaller something is, the less surface it has, the less that pressure can affect it. And that's why life starts getting really weird at the bottom of the ocean. And again, it's also why we don't make submarines super big most of the time. So, volume affects mass, and surface area affects how that object tends to react to the pressure that's acting on it. Does that difference sound okay? All right. Now, there's one more comparison between the two. No, wait, density. Yeah. I gave you a formula for density, so we'll practice the density formula very quickly. I mentioned that different materials all have different densities. For example, if I had a brick of wood and a brick of lead that were the same size, which do you think would be heavier? Lead, and that's because you know that lead is very dense. The same volume of space will be heavier if it's made out of lead, because lead has a lot of material jammed into it, whereas styrofoam does not have a whole lot of material jammed into it. Different substances have different densities. For example, the density of iron is 7,870 kilograms per meter cubed. If I had an entire meter cubed block of iron, it would have that much mass, which is, you know, a lot. Meanwhile, silver's density is 10,500, so a brick of silver the same size would be about a third heavier, even if it's the same size. And then a brick of platinum the same size would be about double that, because platinum is twice as dense as silver. So knowing what something's made of and knowing its density can help you figure out what things are made of, because an issue that has plagued scientists throughout history is that a lot of metals tend to look pretty similar. A lot of them are just gray. And so sometimes you have to use density to help figure out what they're made of. For example, let's say you have a brick of unknown metal. Volume is 0.25 meters cubed, and its mass is 2,625 kilograms, which is heavy. That's like a car. No, that's more than a car. And that brick would only be about yay big. What is the density of this material?
10,500.
Say it again.
10,500.
Yes, 10,500. Density is mass over volume. So 2,625 over 0.25 is 10,500 kilograms per meter cubed. And so checking something's density informs us that this particular brick is made of silver. So, old-fashioned way to identify what stuff is made of. Similarly, if you know what something is made of, and you know how big it is, you can also figure out what its mass should be. I'm not going to be the one to haul this boulder around, but I can at least tell someone what its mass should be if I know it is made of this density of granite, and I know how big it is, you can use the density formula to figure out what its mass should be. So, it's been a useful trick to understand density throughout history. Density is going to matter again because it's going to determine mass in conjunction with volume, and the density of fluids is going to end up affecting fluid pressure. Any questions before I go over one last thing before we break? Okay. So, again, volume and surface area are not the same thing. I want to kind of contrast them very briefly. Why did I do that? Let's say I have a cube that is 1 meter by 1 meter by 1 meter, which is very big. I'd like to very quickly calculate the volume and surface area of that cube. So again, 1 by 1 by 1. The volume of that cube is going to be 1 meter cubed, very literally. Just 1 times 1 times 1. So 1 meter cubed is a very big amount of space. Now, what would the surface area of such a cube be? 6. And what would the unit on that be? Meters squared, because we are taking meters and squaring them instead of cubing them. And this is because area is flat, whereas volume is 3-dimensional. So that's the flat surface area of this cube. This, in conjunction with density, will determine its mass. This determines the surface area that pressure can act on. Now, what if we make the cube bigger? What if instead of 1 meter on all axes, it's instead 2 meters on all axes? So, the height, length, and width are all twice as big. How does that change this? Volume is now going to be 2 cubed, and 2 times 2 times 2 is 8. This new cube could fit 8 of the previous cubes within it. Meanwhile, its surface area, 6 times 2 squared, 2 squared is 4, so 4 times 6 is 24. Now the cube is bigger, so both numbers grew. That makes sense, right? But did they grow at the same rate? We have made the cube twice as big in every direction. By what factor did its surface area increase? It went from 6 to 24. What is that times? 4. Very good. The area got 4 times as big. How much bigger is the volume? 8. The area quadrupled, the volume octupled. The volume grew faster than the area did. And so the pressure now has 4 times the surface area to act on this thing, but now it has 8 times the volume. And that means it's also going to have 8 times the mass. Because if it's still made of the same thing with the same density, that 8 times as much volume will have 8 times the mass contained within it. And this trend only continues if we instead have a 3 meter cube. My drawing senses are deteriorating apparently. If it was 3 meters on all sides, volume is 3 cubed, that would be 36. 9 times 3. The area, 3 squared. So 9 times 36, no, 9 times 6, 54.
Is that 27?
Is it 27?
Yeah, 9 times 3 is 27.
Oh, my bad. Teachers have brain farts sometimes. Thank you, guys. So, they both grew again, but again at different rates. Previously, the volume has always been a lot smaller, but now it's caught up to about half the number. The volume grew exponentially once again. This is 27 times the volume, whereas this is only 9 times the surface area. Volume and surface area do not increase at the same rate, and so that means that the pressure acting on something will be multiplied. Well, the pressure will have times for the surface area to act on something as it doubles its dimensions, but the volume will octuple if you double all of its dimensions. This phenomenon is called the square cube law, and it's one reason why we don't have dinosaurs anymore. Because if a dinosaur is just, a crocodile, but 10 times the size, 10 times bigger, that crocodile is going to have 1,000 times the volume and therefore 1,000 times the mass if you make it 10 times bigger. 10? 100. Yikes. 10 times bigger. My brain is not braining today. 10 times bigger, octuple. Cube. Yeah, 1,000 to the third. 10 times bigger, 1,000 times the mass. And that's why we don't have giant animals nor giant robots. Because the bigger they get, the exponentially more mass they have and the heavier they get, to the point where they can't support themselves. So, that ends volume versus density for today. My goal for Friday is to talk about how these things now affect. If you have any questions, please have an excellent day.